All right, awesome. So a couple announcements. The first was the seminar series, which we got to already. The second is that our first midterm is scheduled for September the 9th, in a week. But what I would like to do is move that back one day because we're moving just a little bit slower than I thought we would. So for that midterm to come at a logical time in the sequence of topics for our course, we'll move that to the 9th, okay? So just one class later, so it'll be a week from Wednesday. What I have done in the past is posted a review sheet which has a series of questions on it. And then, you take those questions and you go look them up yourself. And if you're feeling good about those questions, then you should be in good shape for the midterm. And those are open-ended questions. They're related to different themes. So I might ask you, like, what's the difference between a command and control approach to environmental policy as opposed to an approach using as opposed to a market-based approach, right? I might ask you that. And so if you feel good about that, then you'll be in good shape for the midterm. But the idea is that those questions kind of guide your review essentially. So I'm going to be putting those on Moodle. I'm going to wait just a little bit because I'm not sure exactly what will be through on Monday, but I'll hope to put that up by this weekend. All right. And just as a reminder, so midterms, I do some multiple choice, some short answers, and then you choose one of two essays. So I don't know what kind of advice you've gotten when it comes to studying for exams in the sciences. But to be honest, it's kind of like learning a foreign language. I mean, there's a lot of new terms that come at you. So what I would recommend that you do is, first of all, go through and learn the terms. Now, I've suggested already looking over your notes once a day, once every couple of days. As you're doing that, take note of those terms that you're not quite clear on the definitions of. And that way, you've got time to ask me, right? You can come to my Zoom office hours. I get lonely just hanging out me in my office, right? So come to those Zoom office hours, ask me a question, get some clarity. Then once you've learned all those terms, start thinking about how they connect. How do they relate to one another, right? So when you're studying those terms, you might say that's how you prepare for like a multiple choice question, right? Being able to define those terms. But then to prepare for a short answer or essay question, you got to start thinking about how those terms connect together, right? What are the themes? What are the big questions that they fall under? So that's really what I recommend. First step is being able to define all the terms. The second step is starting to connect the dots. And those review questions that I'll put on that sheet will help you with that. Cool. Any questions about the structure of the midterm, what that's going to be like? Our larger celebration of knowledge? It's going to be a big celebration. We have a lot to celebrate. Cool. So anyway, at least you're familiar with the format, and good luck with your studying. Again, drop by my office hours. Again, these lectures are all on YouTube. So right, I suppose a step that you guys have that classes in the past haven't had is that you can go to the YouTube channel and look up the lecture to see if you missed something in your notes. So that's probably a first step. Although it'd still be great if you came to my office hours because, I get bored. All right, awesome. So last time we were talking about environmental policy in the States. And just to review, what characterized sort of early environmental policy in the United States? How might we characterize the earliest environmental policy of the US in sort of this late 18th century into the 19th century? Maybe we could just think a little bit about that. Exactly. Little to no regulation of resources. Resources were viewed as limitless, and so this movement westward encountered what seemed to be limitless resources. And then that started to transition just a little bit. We saw some evidence of resources running out. We saw evidence of pollution. And ultimately, that led in the late 20th century to a big raft of environmental legislation that was enacted. And so just four that I highlighted, the Clean Air Act was the first one in 1963. Then NEPA, the National Environmental Policy Act. That was a big one. Can anybody recall what it was that was significant about the National Environmental Policy Act? What was it that did that significantly changed how our government looked at the environment? Absolutely. So any action by the federal government that would potentially impact the environment required an environmental impact statement after NEPA came along, the National Environmental Policy Act. The Endangered Species Act was real important, and we'll talk about that later in the class when we discuss wildlife conservation. And then this batch that came along in 77, the Clean Water Act is really the one I wanted to highlight there. And we'll talk a little more in detail about what the Clean Air Act does and the Clean Water Act does when we talk about air and water pollution. But suffice to say, the other thing that NEPA did was after 1970, we had the Environmental Protection Agency, which consolidated all of the agencies tasked with conserving the environment, protecting the environment in the US. And so both the Clean Water Act and the Clean Air Act are ways that the federal government works with state and local governments to ensure clean air and clean water. All right, any questions about that so far? Just doing a little review here, because as I mentioned, we shifted gears a bit in the middle of last class. And then the final thing that we looked at, we contrasted a command and control approach to environmental policy with one that would incorporate economic policy tools. Can anyone share a couple words about the difference in those two approaches? What are we looking at as far as a difference in those two ways? So they're both trying to do the same thing. They're trying to maintain environmental quality, but sort of two different philosophical approaches to doing that, if you will. What's the difference there? Yeah.
Because it was more like giving them a benefit to being
Okay, yeah, absolutely. Top down versus one that uses more market-based approaches. Anything to add? Okay, that's what happens when you put your hand up right after someone else. Right, so command and control, right? Set strict regulations and then has strict fines and punishments for failing those. And economic policy tools exactly try to essentially let the market make it beneficial to preserve the environment. All right, and then we got into chapters 2 and 5. And so now again, we shifted gears into ecology. So this is ecosystem ecology. And we talked about this idea that for any kind of work to get done, we need energy. And that includes, of course, in our ecosystems. We think of all the species moving around, all the things going on. We need energy. And we sketched out this model of energy flow in an ecosystem, beginning with our primary producers, moving on up to our consumers. And we left off at the bottom of this food web talking about autotrophs. And so again, what are autotrophs? Right, autotrophs make their own food. So they get their own energy from the sun or chemicals, and then they store it in carbon compounds. And as I mentioned the other day, if we were autotrophs, all we'd have to do is, the most common example, right? Sit out in the sun to acquire our energy. It's crazy. You look at the green color of these plants, right? And they're green because of this chlorophyll molecule, which is capturing these packets of energy, these photons of energy coming down from the sun. And they're taking that energy and they're storing it in these carbon compounds, right? And then we can come along and we can eat those. So can you think of any examples of autotrophs that don't rely on the sun? Anybody know of any examples? Fungus. So fungus are interesting. Fungus, most of them, well, all of them, are a little tricky to put in the food chain because most of them are detritivores. They feed on like dead or decaying matter. So we're going to put them in a different category in just 1 second. Yeah. So phytoplankton they're definitely, so they're aquatic, but phytoplankton are actually doing in the ocean the same thing that these plants are doing on land. They're green. Like, do you ever see a pond that has a real green color? Like maybe it's like too fertile. So phytoplankton are different from these grass, but they're still doing photosynthesis in the water. Yeah.
I guess kind of similar to what you said, but like the deep water vents, like the heat vents, where there's the small organisms that require energy for heat.
Yeah. So one of the first examples of a whole community organized around energy that didn't come from the sun was actually in these deep sea thermal vents. And these were discovered in the 1970s. And you know, most of the bottom of the ocean is really boring. I mean, you guys have seen the movie Titanic, right? You're just going along at the bottom. It's like nothing. It's just like gray, gray, gray. Then all of a sudden, there's this ship. And then it becomes colorful and all these things. Well, that's not real. You know, the bottom of the ocean is not very productive. Why might the bottom of the ocean not be very productive? Any thoughts? No sunlight, right? So all of those autotrophs that require sunlight, they can't grow. So for there to be energy and a community on the bottom of the ocean, they have to feed on stuff that's essentially died and sunk down to the bottom. Except for some places where the continental plates of the Earth's crust, where they come together, they release a gas. They release hydrogen sulfide gas. And where they release that gas, there are bacteria that convert that hydrogen sulfide gas to sugars, the same way that plants convert sunlight to sugars. And then there's a whole community of animals organized around that. So this is a picture on the bottom of the ocean. So imagine, you know, when these things were discovered, the submersible is just moving along the bottom of the ocean, transmitting these images. Person's probably like half asleep up in the ship, watching the screen, looking at it. And all of a sudden, something like this shows up. It's like a forest of these crazy tube worms. They've got these white shells and these red plumes on the top. And these red plumes are full of these bacteria. And so these tube worms use these bacteria. The bacteria take the gas, turn it into sugars, and then the tube worms use those sugars to run their bodies, essentially. And so it's what we call a symbiosis. It's a close relationship between two species, where these bacteria produce sugar. So all of a sudden, in the middle of the dark, ice cold bottom of the ocean, we have this crazy community that has autotrophs that don't need sun. All they need are these chemicals, this hydrogen sulfide chemical. And so it's kind of neat. So then you have this community of tube worms, and then like that's kind of like the law of nature. Like once you have something, like something else will eat it. Something else will connect to it. And so if we look, and you don't need to know all these names. I'm just showing you what this community looks like. So if we look at a community in these deep sea, they're called hydrothermal vents. Hydro, of course, water, and thermal just means this is really warm water that's coming out from under the ground with these gases contained in it. So we've got this whole community with these tube worms there, and then we've got some fishes that come by, you know, because these tube worms are going to die, and as they decay, we've got things that eat them. We've got shrimp, we've got freshwater mussel, we've got ocean mussels, all these other things, and so this whole community is living there in the dark on the bottom of the ocean, And we didn't even know about these till the 1970s. I don't know. They say we understand the surface of the moon better than we understand the bottom of the ocean. We've explored more of it, so I don't know. What else is there on the bottom of the ocean? Maybe you guys will figure that out. So anyway, just a different example of an autotroph, of a producer. So heterotrophs then, as we talked the other day, these are species that acquire their nutrients by consuming other organisms. And so this is the majority of species then. These cheetahs are acquiring nutrients at the expense of other species, right? It's kind of like the circle of life. So heterotrophs, these include things as tiny as worms, and then, of course, as large as things like whales and organisms like that. Okay, so we've got autotrophs out there, and we've got heterotrophs in our communities. So the question about fungi was raised earlier, and how do they fit into this? It's a good question. You know, fungi are one of those groups of organisms that we don't know a lot about. We're still learning a lot about them. You know, there are fungi that break down crude oil. There are fungi that break down contaminants like PCBs. Fungi do incredible things in the ecosystem. We're just learning about them. But fungi are an example of organisms that feed anywhere in the food chain on whatever is dead. We call these detritivores. So detritus is just a name that biologists use to refer to decaying organic matter, right? So these are species that we can't really fit into like a trophic level in our food web real neatly. So we've got birds, we've got insects, we've got other things. This actually reminds me of something that happened to me. I was in the airport. This is a couple of years ago. This is, back before all the COVID stuff. So I was waiting in line to get on the plane, and there was a raven in line. I mean, he had his, had the passport, the ticket, everything, but he was holding on. It's kind of hard. He was holding on with like one claw, kind of. It was like a dead rat. And the flight attendant was like, "I'm sorry, you can't take that thing onto the airplane." And the raven said, "Why not? It's carrion." Carrion is a word that is used to refer to dead animals. So, but I don't know, but still, they didn't let it on. Which I thought, I mean, I guess if you've got wings, you can fly on your own. But I don't know if you've had anything similar happen to you. Now, why are these important? Why are these detritivores important? Any thoughts? What function do they fulfill in our ecosystem? Okay. Yeah, right. So back when we talked about economics and like that we can take the waste of one process and cycle it back to nutrients of another. Yeah, they're turning all of that waste back into nutrients. So what's going to happen here, probably in about a month, is all these crazy photosynthetic devices are going to start falling off of trees, right? Those leaves. And what keeps those leaves from piling up taller and taller and taller every year are these guys, right? The detritivores. I can't even say it. So if we didn't have these detritivores breaking down that organic matter, it would accumulate and cover the earth. And we wouldn't have the nutrients available for our plants to grow the next year. So these detritivores are super important because they break down this organic matter and make it available to plants the next time. So yes, we kind of said that already, right? So they make nutrients available to the producers. They're kind of like, I don't know, like they're not like the glamorous species. Like they don't have their own like Nat Geo specials. Like they don't have their own Animal Planet characters and stuff because they're kind of doing the dirty work. But they're important in their own rights. They're important in their own rights. Give them some props. All right, so it turns out that when we actually look at the arrangement of connections among trophic levels, it doesn't look exactly like a food chain. It looks a little bit different. This is an example from the African savanna. We've got our producers down here, some grass, we've got a tree. We've got our primary consumers, a bunch of things, and then some termites as well. Then we've got our secondary consumers up here. Now, how does this model differ from our food chain? What are the differences here? So it resembles what we call a web. And just thinking about like those links, what about these links are different from the food chain? How does our model here look a little different from the food chain? Oh, animals eating what? Exactly. We have animals that are eating different things. And we have the lion, which appears to eat about everything. There's a hand up over here too. Yeah, so first of all, we call that omnivory, right? So omnivory is when species feed on more than one thing. And again, if we look at the lion, it's not only feeding on things on the primary consumer trophic level, it's feeding on things in the secondary consumer trophic level. So we have omnivory, which means that we've got arrows going different, coming from different sources to one consumer. The other thing is that we've got a lot more than one species on a trophic level here. And so that's why our realistic model is more spread out. It's not so vertical, it's spread out horizontally, and we've got lots of species on each trophic level, right? You look at all these different species, they're all primary consumers. These are secondary consumers, or we might call them primary carnivores. So here's a question for you. Okay, first of all, how many trophic levels do we have here? 3. So three trophic levels we have. Can anybody guess? We can move all around the planet. You can go to North America, Africa, South America, Asia. You can look on land, you can look in water. Does anybody know what the maximum number of trophic levels we see is? Anybody just want to take a guess? I know you have no reason to know this answer. Any guesses? 5? That's right on. Was I doing this? Just intuition, right? So 5 is about the maximum number. We don't get up above that, which is actually a good thing, because what that means is that what our top carnivore looks like, say it's a lion, it means we don't have any species that eats those, which is probably good for us. And we don't have anything that eats those, which again is probably because we're getting into like T-Rex territory here, right? So globally, about the maximum number of trophic levels we see is 5. So why is that? What is it that limits the chain length of a food web? What limits us globally to about 5 trophic levels? Yeah, exactly. So if we look at this height, the number of trophic levels, there's 2 things that are going to come into play here, both of which relate to energy. So when I normally teach this class, it's in Rhodes Robinson Hall, and we're near the physics department. And I say that, we have to understand these laws and not break them, or like the physics folks are going to come and arrest us. But so we have to go back to the laws of thermodynamics. So anybody know what the first law of thermodynamics is? Exactly. Yep. So first law of thermodynamics tells us that in a closed system, energy can't be created or destroyed. It can only be transformed. Now, this may give some of y'all a funny feeling, because do we think that Earth or an ecosystem is a closed system? Yeah. So that's a good point. So when we look at like matter, like the elements that are contained on Earth, that it's sort of a closed system. But then when we think about energy, like it's always coming in from the sun, but it's coming in at about the same rate, approximately. So when we look at how much energy is available every day, it's kind of sort of, the same. So what we might say is that the supply of energy is pretty much constant. Okay, so we can't create or destroy energy, we can transform it. Anybody know the second law of thermodynamics? And this relates to the point about energy loss among trophic levels. Yeah, it relates to entropy, and we can state it most simply by simply saying that energy conversions are not 100% efficient. So we can convert energy from one form to another, but each time we do that, we're going to lose energy to entropy or to heat, right? So if we think of the energy available to an ecosystem as being everything that those producers capture and turn into carbon, that's what we've got to work with. And then as that converts, as it moves up the food chain and food web, we're losing energy at every step. So this is sort of a cartoon that makes that point. So if we start with plants, and our y-axis here is the amount of available energy. As we move up from plants to herbivores to carnivores, and we keep going up the carnivores, our energy is going down and down. Now, this is not drawn to scale. Has anybody heard an estimate of how much energy from the trophic level below is actually captured in the trophic level above? Yeah, as an estimate, it varies with a lot of things. But as an estimate, it's estimated that 10% of the energy in our plant trophic level is available in our herbivores. In other words, we lose 90% with every shift up the food web. So clearly this is not drawn to scale. This is almost the opposite. This almost shows maybe 90% moving up each trophic level. But in reality, we're losing 90% each time we move up. So as you can imagine then, by the time we've moved up 5 trophic levels, there's not much energy left. There's not a lot of energy for a Bengal tiger to consume. But there's a lot of energy for the deer to consume, right? So because of that, we have fewer and fewer individuals as we move up and up and up in the food web. Now, another point I want to make here, you'll notice that what does it mean that we have sort of a downward sloping top to each of these? Anybody have any thoughts? Why isn't this like a perfectly horizontal thing? What does it mean that it's moving down? Any thoughts? Yeah, so we're losing energy even like within these trophic levels. So, right, so this part here is telling us that even before we're moving from trophic level to trophic level, we're losing energy within them. And so it could be because they're not able to eat everything in the trophic level below them, for instance, would be one reason for that. So there's the available energy to the trophic level above is less than the energy that entered that trophic level. So yeah, and so then B here, the shift as energy moves from one trophic level to the next, right? That is that 90% loss that we're talking about. And this is a figure out of your book. Hopefully you can get to your book and check this out. If you can't, you're going to be able to zoom, I hope. Or you can just look at it on YouTube. Have I told you this? Like when I explained something and it was really complicated, I tell my students like, oh, just wait till it comes out on DVD, like kind of joking. And now I can actually say, well, you can just go watch the video. It's like you didn't understand it this time. And you still may not understand it after that, but you know. Okay, so we have this term, it's called trophic level transfer efficiency. This is one of those words. So, this semester is different, right? Because we're all going to be done with classes before Thanksgiving. But it used to be that you go home for Thanksgiving and then come back for like the end of the semester. And I always told students, when you're having a conversation around the dinner table or wherever you're having the conversation with the people that are paying for your education, try to use some big words in that conversation, to show them that like they're getting their money's worth of their investment in your education. So, like if you're hanging around, the Thanksgiving dinner table, and you can use trophic level transfer efficiency at some point in the conversation, they're going to be like, yeah, that interest in environmental science course is worth it, right? So this is one of those big words. But all it's saying is that the amount of energy that moves from one trophic level to the next is very low. So here's a little cartoon of a squirrel, and it's eating. I love that it's eating a peanut, like the natural food of squirrels is a peanut. But those of y'all that can see, what is this cartoon trying to show us? Any thoughts? This one you get to test your eyesight if you're like a mess out of there. Take out your telescope and analyze this figure. So we've got 1,000 joules of energy in this little peanut. Where's most of that energy going? Yeah, so about 80% of that is going to cellular respiration. So, the majority of the energy that squirrel takes in is just being used to maintain its body, to keep its body running. All right, and then about 20% of that is waste, the species. It's not even incorporated in the body or the metabolism. But only about 1 to 2% of that energy actually goes to growth of that squirrel. So when we think about why we're losing so much energy, right, the first thing to keep in mind is that a lot of the energy that's consumed from one trophic level is not directly converted into biomass of the next trophic level up. We've got some like strange squirrels on this campus. Have you guys seen? Like, I don't know, like they're not afraid of people is the first thing, which I mean, I guess that's okay. But have you noticed in like a lot of like the trash cans, they've like chewed little like entryways? Yeah, I was walking out of Rhodes Robinson one day, and literally as I was walking, it's like the end of the day, I had something else in my mind. The squirrel came like flying out of that trash can. I swear, it just went shooting out and like landed 3 feet away and then ran away. It was really weird. So I think someone needs to do further research on like squirrels at UNCA. The school that I was teaching at in Texas previously, one of my students actually, this is sort of sad, sort of funny, maybe mostly sad, I don't know, actually ran over a squirrel on their bike, like driving across campus. Like the squirrel was so not afraid of them that it like, and they tried to avoid it, but it like, because squirrels, they look so confused, they run out in the middle of the road, they're like, and then, but they should really move and they don't. I'm sorry, the squirrel, it just brought out all these ideas. Then the other thing, as was mentioned, is that organisms are rarely even able to consume all of the energy in the trophic level below them. So here's a lion with a zebra, and you look at the carcass of that zebra, and a lot of that is not going to be consumed by the lion. What's going to happen to the rest of that carcass? It's going to decompose, yeah, and you'll have some other carnivores, you'll have hyenas and things that'll come in here. But then a fair amount of that is also going to just be decomposed. So the other reason that we lose a lot of energy, trophic level to trophic level, is because in most cases they're not able to use all the energy in the trophic level below them. Questions or comments on that so far? All right. So So this results in what's called the pyramid of numbers, which really should be a game show, but it's not. It's a model of energy flow, and it was first described as the Eltonian pyramid. You don't need to know all of this, but Charles Elton, he was actually at University of Georgia. He was one of the first ecologists, and to get at what that is, let's ask a simple question. Let's imagine we're looking at a small pond, and let's just say that it's small enough that we can count all the individuals of each species in this pond, okay? So if we do that, it looks something like this. We can look at our producers here. So this is an example of a phytoplankton, actually. Like a protozoan, it's green, so we know it's photosynthesizing. Most things that are naturally green are photosynthesizing, unless they're animals like iguanas and chameleons. They don't photosynthesize, but they just look green. Okay, so we've got millions of protozoans are producers. And we've got hundreds of thousands of these daphnia, which are also plankton, but they're small animals. Then there are hundreds of beetles that feed on those daphnia, and then tens of fish that feed on those beetles. So this pyramid results from low trophic level transfer efficiency, right? And again, this is not drawn to scale, because if we were losing 90% each time, we'd start out with a bar like this wide and then get like really tiny. So the pyramid of numbers is this idea that we have progressively fewer individuals as we move up the food web. Now, what is this term biomass? What does that mean? Any thoughts? You guys know that feeling when like you don't know something and you're about to know something, and then after you know it, you're going to know it for the rest of your life? I kind of get that feeling now. Isn't that cool? So biomass, so bio is just life, right? Bio, and then mass is just the mass of things. So it's just like the mass of living matter, essentially. So it just means if we were to go and weigh all the protozoans in the pond, all the daphnia, all the beetles and the fish, we could get the biomass of each trophic level. Now, any idea why it might make more sense to talk about biomass in each of these trophic levels than the number of individuals? What do we think about that? Yeah. So the body size of these things is way, way different, right? So these protozoans are microscopic. These daphnia, you can see them with the naked eye, but just barely. Beetles are small, fish are bigger. But yeah, if we're going to talk about the amount of energy, you know, you could fit hundreds, if not thousands, of protozoa in the same mass as one individual fish. So really, what we probably want to do when we're thinking about energy flow, instead of thinking about the individual numbers in the population, we think about how much biomass is in that trophic level. Does that make sense? Okay. So, do we always find less biomass at higher trophic levels? Now, the way that I asked that question, you might just think that the answer is no. So, you know, the budget's been tight lately. I was going to take the whole class down to the Bahamas. We're going to do some research. They said, sorry, Dave, we can't give you the budget for that. But, you know, here's a budget to take some photos and stuff. I'm like, all right, it's just as good, really. So imagine that we went out to the open ocean. And imagine that we could take a gigantic cylinder and just like chunk it down in the water column. And then in that cylinder, we could count like each type of species, their trophic level, and their biomass. If we were to do that, this is what we would see. It's flipped over, you guys. What the heck is going on? So these are real data. It turns out that when you look at the biomass per square meter of producers, phytoplankton, it's like a quarter the biomass of herbivores, right? The zooplankton, that second trophic level. And that's even less than the biomass of fish. These are real. I'm not making this up. I'm not making this up. Last 2 semesters ago, the class went down and we collected the data. No, sorry, I don't want to make you sad. So just chatting with your neighbor across these annoyingly thick and solid plexiglass barriers, or like whoever is nearby that you can talk to. Just take a couple minutes and think about this. Don't just think about it, talk about it. How is it possible for a small amount of biomass on a low trophic level to support a large amount of biomass on a higher trophic level? What's going on there? So think about 5 minutes, think about how this might be possible, and then we'll get back together. And salmon are not involved here. I'm going to tell you right now. You can't just be like, it was the salmon. So think about 5 minutes, just think about how this is possible. There. And I'll say it again for all of you listening at home. So it turned out that what was happening is that the really high rates of reproduction at the bottom of the food web were causing there to be like more energy produced per unit time than up at the top. So if we took a snapshot at any given moment of how much energy was in each trophic level, it looked like we had more at the top of the food web. But we were missing the fact that the lower trophic levels are reproducing really rapidly. But unfortunately for them, what was happening as soon as they reproduced? Why didn't their biomass accumulate really fast? I think I heard someone say it because they were being eaten. This is one of those truths that parents of phytoplankton and zooplankton, they just try not to bring it up with their kids. They just, your life is probably going to involve being eaten. Oh, something got me. No. So, sorry. That's why I'm not an acting professor. I'm an environmental science professor. So these are just reproducing so rapidly that the supply of energy is higher on the bottom, even though the amount of energy at any given point is not. Does that make sense? Kind of, sort of? Yeah.
So even though there's more scissors and herbivores, there's still less biomass.
Right, exactly. So they're producing a lot in a given day, but the vast majority of that is eaten as soon as it's produced. So that's why there's a lot of energy in a given day produced at the bottom of the food web, but it's almost all eaten and moved on up the food web. So really the main point there is just that when we're talking about energy, for our models to work, for it to make sense, we have to talk about the amount of energy produced like in a given time period, right? So we want to be sure and think of energy as the amount produced per given time. Okay. So this is an interesting thing. So what we can do then is we can look at an area's net primary productivity. And the way that we calculate net primary productivity is we look at the total amount that's produced. So like the total amount of energy that our producers are capturing from the sun and turning into sugars. And then we subtract the amount of that energy that the plants need to use to maintain their own bodies, right? Because you might not think of it, but plants, especially trees, right? They're transporting liquids and solids throughout their plant bodies, so they do need to burn up some energy in the process. So we can look at, for instance, this forest. And we can ask the question, in a given day, how much energy is that forest producing? Now, how might you measure that? Any thoughts? Like if we were going to try to measure that, what would that look like? Like how might we go about doing that? Any ideas? Mm-hmm. So we could look at heat. Yeah, I guess we could look at some. Yeah, so if you looked at, yeah, so that would get us, that would certainly help us with this respiration rate too, to tell us how fast the plant's burning up that energy. Yeah, so it turns out that the actual rate of productivity is hard to measure, but we have a way of approximating it. And so what we usually do is we estimate the amount of grams of dry plant matter produced in a square meter per year. Now, often when I teach this class, there's a big window right next to us, and we can just look out at the quad, and we can imagine measuring this for the quad. And the way we would do this in the quad is we would measure off, say, 1 square meter of grass in the quad. And then we go maybe every week and we clip the grass. And we dry it and we'd weigh it. We come back the next week and do the same thing. And then over the whole year, we get an idea of like how much energy was produced in that square meter of quad. Now, it's a lot easier to do with grass. You can imagine with trees, it's a pain, right? Because the trees have been growing for years and years. And so you have to estimate how much was here now, how much was here before. But this is what we look at when we look at net primary productivity. So we can do a really cool thing then. We can look all around the globe and we can see where is net primary productivity high and where is it low. And so this is it's a cartoon looking at net primary productivity on land and on sea. One of the things you'll learn about me is that I love maps. So this is just one of many maps you'll see during this semester. But let's take just a minute or so to look at this map, and think about what are some take-home messages. What are some conclusions that we can glean from this graph? I keep saying graph. Figure. Okay, so there's one, right? We look at these warmer colors of highest productivity, and if we were to draw a line where the equator is, it would intersect a lot of these areas, right? It's going to be right through here, right across there. It intersects a lot of these. Good. What's another conclusion we can draw from this? What do y'all see here? Yeah, it's interesting, isn't it? That in general, productivity is higher on land than in the ocean. And a lot of the open ocean is not very productive at all. At all. And so for species to live in the open ocean, they've got to cover a lot of ground to eat, to find all they need to eat. Yeah, it's interesting, right? The open ocean, not very productive. In fact, if we look at the Sahara Desert in North Africa, a lot of the open ocean is at about that level of productivity, isn't it? Anything else? What about where we are? What's net primary productivity like in the Southern Appalachians? Those of y'all that can see. Oh, you're throwing a number out there. I was just thinking like relative to the rest of the world. Pretty high, right? Yeah, so we're over here. I'm not sure quite if we're touching that right. We probably are. So based on this map, what do we think determines high levels of productivity on land? So if we think of, so we're measuring, yeah, so we're measuring basically plant mass here essentially, right? We're measuring plant growth here. So I don't know how many gardeners are in the room here, right? But what do plants need to grow? Well, they need light and they need water and they need some other things too, nutrients and those kinds of things. But it turns out, so thinking of water and temperature, does it look like a lot of these areas of high terrestrial productivity are in warm areas? I see a couple nodding heads. Yeah, I mean, there are a few exceptions, but in general, pretty warm. So it turns out that on land, net primary productivity increases with temperature and precipitation. So the more rain you have, the warmer temperature you have, the higher NPP you have. And you know, here we are in the southern Appalachians, we get a lot of rain, and relatively speaking, it's pretty warm too, right? So these, you know, we've been getting a lot of rain lately. In fact, a couple of years have been way up above normal. But that leads to high productivity here. As you move further west, productivity drops and drops and drops. And that's because precipitation drops and drops and drops. Even though temperature is increasing, you got to have both, right? Now in the water, this may be hard for you to see based on where you're sitting, but there are just a couple areas of real high marine productivity. And it's already down here, you can see. But clearly in the marine realm, you don't need rain, right? You got all the water you need. What you need is sunlight. And for us to have plant communities growing on the bottom of the ocean, what has to be true for the sunlight to penetrate to the bottom? Fairly shallow water. Fairly shallow water. So this area up here, it's called the Grand Banks Real Productive Fishery Area. Right? Called the Grand Banks. Relatively shallow area. Light can penetrate down to the bottom, and plants can actually be growing on the bottom of the ocean. Some coral reefs as well. We have similar things going on. Now, nutrients are also important, and I'll just share one example. There's some real important marine fisheries here off the coast of Chile, and we have a wind that blows from land out toward the ocean. And so what that does is it blows the surface water away from land. And so then when it blows the surface water away from land, then water on the bottom of the ocean comes up from behind to fill in that area. Now, do you think there's more nutrients in water near the surface of the ocean or at the bottom of the ocean? So it's kind of counterintuitive. You'd think surface because that's where all the photosynthesis is going on, right? But it turns out, what happens to everything that dies in the ocean? It sinks. So strangely enough, there are actually more nutrients in the bottom of the ocean just because that's where all the stuff accumulates that decomposes. So then when that water from the bottom of the ocean comes up to the surface, it brings all those nutrients up to where the light is. And then you have a lot of productivity. So when we look around the planet at where NPP is highest and lowest, again, on land, it varies with temperature and precipitation. And then in aquatic ecosystems, it varies with light and nutrients. Now, why might this be something that we'd want to know about as environmental scientists who are studying people's relationship to the land? Any thoughts?
Well, it stands to reason that like humans would be in the areas where there's higher NPP because that's where there's more nutrients, but at the rate in which we deplete our natural resources, I guess we would eventually be taking the global NPP down. Where it's already the highest.
Yeah, so it's interesting to think about, right? If we're just living off of the land, then we should be living in these areas with really high NPP, because that's where the plants are going to be growing faster. That's where we'll have more productivity on all our trophic levels. But of course, now it's a little different, right? Like now, if you go to the grocery store, I don't know, maybe your apples come from New Zealand, maybe your grapes come from Chile, maybe your beef comes from, wherever, all these different places. So we're all connected here now. You might argue we've kind of created like a global food web, really. But back in the day, the places that people could live was limited by the productivity, right? By the land's ability to produce nutrients, because of course we're consumers, right? So we can do kind of an interesting thing here. We can look at how much of the net primary productivity in an area is used by people. One thing I'm learning about this room is how the lighting is. Can you see that figure okay? Or should I try to turn off this front bank of lights? Can you see that okay? So this is a cartoon that looks at what percentage of NPP is used by people. And so the coolest colors are so 0 to 10% is the blue. Greens are up to 45% to 50. Then these warm colors, orange is 100 to 200%. And then purple is anywhere between 200 and 40,000%. You mean just for the last category or like as a whole? So my feeling is probably there were only a few spots where they were using like thousands of percents of NPP. So my guess is instead of making a separate category that might be real tiny on that map, they probably just broadened that category to include like a reasonable number of locations. But that's an interesting question. It would be neat to know which place it was that's at 40,000%. So just take a minute or so to look at this and think about, again, what's the take-home message for this figure? Okay. Yeah, so India and portions of China, right? Eastern China, very high. Other observations from this figure? Yeah. So, yeah, good question. So, right, so like thinking of like where we grow cattle, for instance, if we go back to our last figure. In the Midwestern United States, it's fairly productive, right? That's where we raise a lot of cattle. And interestingly enough, animals are grazed all over the world in the areas that used to be grasslands. So for instance, the Midwestern United States, what's called the Cerrado in Brazil, the savanna in Africa, and then there are grasslands at higher elevations in Asia as well. So like all those places, like we've started grazing animals. So yeah, so this, right, so if I'm raising cattle and say shipping it to a market somewhere, then that would still count as like I'm using the productivity, you know? So let me ask the obvious question then. How is it possible for us to use more than 100% of the productivity in the area where we're living? So yeah, you could definitely say we're using too much. How is it possible? Let's say that the place that I'm living, let's say there is, I don't even have the units on this, 200 grams of plant matter produced per centimeter per year. But I'm using up 400. How is that possible? Yeah, so if we're harvesting more than a year's worth of productivity, or if we're bringing stuff in from other places, then we can live in one locality and use more energy than is produced in that place, right? Like, you know, who knows what productivity is like in the land, over on West Asheville where I live, I don't know. I mean, we have a garden, but we eat a lot of stuff that isn't grown in that garden. So we're definitely consuming more than that land itself produces. So by bringing stuff in from other places, we can consume a lot more than the land itself produces. Yeah. So where are the areas of highest productivity? So I mentioned, where are the areas that humans use the highest percentage of productivity? You mentioned India and China. Any other places? I don't know if you can see in the US so much. What part of the US are we using the most percentage of NPP? Northeastern up in here. You may not be able to see this in the back, but there are a few kind of pink splotches. So all through here along the eastern seaboard, cities like Boston, New York, Baltimore, DC, all on down there. Those are areas that consume a lot more energy than is produced. So that means they've got to be bringing it in. They've got to be bringing in enough food from outside to feed everyone. So what we can say is that cities are net importers of energy. And on the other hand, they're net exporters of waste. So to be able to support places that are consuming thousands of times the amount of productivity that's produced there, you've got to produce other stuff and bring it in. All right. Any questions or comments on that?